Foundation Day. So, this is the day when the foundation stone was laid in this main building here at IIT Delhi, and we commemorate this every year with a faculty award ceremony which just got over and followed by a institute lecture. And so we are extremely fortunate to have today Prof Sanjay Sarma from MIT, who's of course a distinguished mechanical engineer. He serves in the mechanical engineering department at MIT, but today he's going to be speaking to us in his other avatar as MIT's Vice President for Open Learning, and that is something which we would really like. We look forward to learning about from Professor Sarma. So welcome to all our delegates who are joining us online. I know it's very early for Professor Sarma in Boston, but thanks for joining us in these early hours. And we look forward to your presentation and have a discussion thereafter. Our colleague Professor Ambuj Sagar will be conducting the session. He's an old friend and acquaintance of Professor Sharma, and Professor Sagar is also the head of the School of Public Policy, also very passionate about matters related to education and learning and so on. So he'll be conducting that. But before that, I would like to request our director, Professor Angpal Rao, to formally welcome the speaker and also share a few thoughts about today and then the Foundation Day and about IIT Delhi.
Thank you, Professor Roy. And I think Foundation Day is also an occasion to remember the old times, how IIT Delhi started. And in fact, it started as College of Engineering and Technology. It was not an IIT when it started in Delhi. It was registered as a society on 14th of June 1960. And the first admissions were made in 1961. The first admissions again were not made as IIT, they were made as into that College of Engineering and Technology. And the students started reporting to the college on 16th of August 1961. And the inauguration happened on 17th August 1961. And then through an act of parliament, IIT, it was renamed as IIT, and then the foundation stone was laid on this day. And that's how the journey began. So today IIT Delhi is about 11,600 students, and we have over 3,500 PhD students. So what it means is almost every third student on the campus is a PhD student. So our transformation from a pure undergraduate kind of an institution to a research-centric institution, I think that transformation is almost complete now. So now we have a lot of research happening on the campus. Even in QS rankings, we routinely figure among the top 50. In fact, our best rank was 38 in the world in terms of research impact. So I think things are only getting better on that front. And in fact, this Foundation Day, we're also very happy to have with us Professor Sanjay Sarma. We have been in touch with him. In fact, we met with him when we were in the US a couple of years ago before the COVID. The topic is also very interesting and something which is very close to all of us in the education space. India also has started or launched the new education policy, and we are also expecting a lot of changes to take place as part of the new education policy. At IIT Delhi, one thing that has definitely happened is we are no longer narrowly focused engineering-centric kind of an institution. Now we have multiple other disciplines. In fact, Ambuj, who comes from the School of Public Policy, that is a new school we started about 2.5 years ago, and that's already doing very well. And similarly, we have Department of Design. Our humanities department has also grown quite a bit now. They are also offering multiple postgraduate programs. So there are a lot of good things that are happening now. And in fact, the abstract of Professor Sharma's talk is also very provocative. And even the title says how engineering education can and should change. I think there are many changes taking place, but I think the resistance often comes from the faculty themselves. Though we all teach technology, engineering, I think the use of technology in education has been pretty minimal. I think the only technology that we have all adopted, on a widespread scale is PowerPoint. I think other than PowerPoint, I don't know what technology has really seen, so much of adaptation. And in fact, I recently read a joke somewhere that a professor and a medical doctor, they both went into coma, and they both came out of coma after 30 years. And the medical doctor goes to the hospital, goes to the operation theater, and is completely lost. There are all these lights and robots and what have you. I mean, everything has changed in the medical profession. And our professor comes out of coma, takes the chalk, goes to the class and starts giving the lecture. So I think that is how the two things have been. But I think one of the things that has also happened during COVID is now people are beginning to realize that we can do many more things than use of a chalk and board. And at IIT Delhi, we started major online initiatives now, which have also picked up very well. In just a year of their launch, we have almost like 35 certificate programs, and we have already reached over 4,000 people, through these certificate programs, which are all online. And I think things are changing. Another 5 years, I would expect a lot more transformation to happen in this space. I think I'm also looking forward to Professor Sharma's talk on what more we can expect in this space. Thank you. Thank you very much.
Thank you, Professor Rao. And I would now hand over to my colleague, Professor Ambuj Sagar, to introduce the speaker and also conduct the session thereafter. So, Ambuj, over to you.
Thanks, Shantanu. And I don't think I need to spend more time introducing Sanjay. He's a man who wears many hats as a mechanical engineer, but even within mechanical engineering, he's done all kinds of different things, including a lot of work on RFID, which normally you wouldn't expect a mechanical engineer to be doing. But more recently, he has really become more and more engaged in questions relating to education. He co-led the MIT study on thinking about the future of engineering education for MIT. He's vice president for open learning at MIT, and therefore oversees a lot of initiatives. But I think he's also kind of it's beyond in terms of delivery of these kind of programs. I think he's very has been thinking quite a bit about really pedagogical questions much more deeply. And so I think all of us are very much looking forward to hearing him. So with that, Sanjay, thanks again for joining us. I know it's early hour for you. So over to you. Thank you.
Thanks very much, Ambuj, and thanks everyone. Can you see me and hear me and see the slides?
Yes.
Great, thank you. So let me start by saying that IIT runs in my veins. If you take my daughter, 2 of her parents are IIT graduates. That's me and my wife, obviously. And three of her 4 grandparents are associated with IIT Delhi. I guess my wife and I are errant because we went to IIT Kanpur. But I used to spend many nights crashing in a my classmate Mukund Rajan's room in Karakoram when my parents had left Delhi. And, my IIT friends, that's the picture on the top left, we're still essentially brothers and sisters who will do anything for each other. So for me, this is a great pleasure and an honor. So thank you for having me. I'm going to kick things off by showing you a video, all right? And it's a video of how kittens learn. Remember that mammals, and especially human beings, make a special deal with nature. That is, we're adaptable. But we're also infants much longer than, say, a spider or a reptile, and humans much more than other mammals. So just watch this video, and then I'll kick into my presentation.
In just 3 weeks. But this is where
I just want to confirm you can hear the sound?
Yes, we can hear.
Yes.
Okay, I'm going to restart, and off we go.
They can't walk. Their eyes aren't even open. Just like the young spiderlings, they are too small to be predators. Growth, however, is rapid, from fluffball to mini predator in just 3 weeks. But this is where spiders and cats differ. Though physically the cats are now quite developed, their predatory programming is incomplete. Now, to start developing the mind. First, their instinct makes them curious. Instinct makes them play. Play links body with mind. They start to look like predators, focused, fast, alert. But at this stage, the rules are simple. Catch anything that moves. After all, they could be anywhere, and anything could be prey. But a cat can't live on feathers and stones. This simple instinct needs a focus. Enter mother. She now comes back from hunts with dead prey. This is the new focus of the kitten's play. The kittens get what she can catch, a sample of the world of prey outside. She is programming the predatory machine, preparing it for future hunting. Sight, smell, feel, taste. This is what should be eaten. For the next stage, live prey. Now the mind is focused on specific prey, a lesson in handling. How fast is it? How does it move? How do you catch it? Without this training, kittens will never be good hunters. This time, the vole escapes. Finally, into the field to put training into practice. They go into the outside world with skills that basic instinct can't provide alone. They have the advantage of learning. The predator hunts, fueled by instinct, fine-tuned by learning.
So this is an old BBC documentary on how cats learn. And the idea is that a cat never attended, kittens never attend lectures, right? But this is our learning instinct. Human beings are not very different. By the way, Michelangelo probably never attended a lecture either. There's a picture of Michelangelo that you can't see, but he never attended a lecture either. He learned in the same way, right? He learned from the masters. Actually, if you read the books of Giorgio Vasari, you'll read about it, about how all the masters in Renaissance Europe learned. We have many fallacies in our education. I'll point out two. The first is, and this is, I think, a killer. The student's mind is a sheet of paper, and the professor has the pen. And all the professor has to do is write on that sheet of paper and declare victory. And if the student doesn't get it, it's their problem. And I'll contrast that with the cat and the kitten, right? By the way, even as adults, we learn the same way as we learned as babies, because that's our evolutionary prerogative. We've evolved to learn that way. The real model is that the student is building a model of the world, and we need to nurture it with scaffolding and examples. That's typo, and examples. And that's what the cat was doing. And this is what we don't do, because we take the former model, which is I'm writing on the student's mind and declaring victory, and there's an exam. And, in fact, when I was a kid, you Muggoos would do well. You pass the exam, you're done. By the way, we also have cognitive psychological knowledge that you forget very rapidly, right? It doesn't internalize. There's another problem we have in academia, which is the streetlight effect. And this is actually based on a joke, which many of you will remember. It's the joke of a young man searching in the dusk under a streetlight, and the police comes to him and he says, "What are you doing?" He says, "I lost my wedding ring." And the policeman says, "Where?" And he points to a region where it's dark, and he says, "Over there." And he says, "Why are you searching here?" He says, "Because wahan pe andhera tha, yahan pe light hai. There's light here." So one of the other sort of fallacies, it's actually a well-known concept, it's called the observation effect, is we teach what we can test because testing has become so important. And if it can't be tested, we choose not to teach it. And as a result, in my view, we have walked away from many of the important lessons we should teach because we can't test them properly and give objective scores. And the time has come to change that as well. We have to teach students how to hunt. And that's going to be sort of an essential part of what I'm going to talk about. So what I'm going to start with is what IIT does well. And or engineering does well, engineering education does well, but really IIT, I'm going to use the focus because IIT is the pinnacle of that. And as I've said to you, I'm a proud IIT alum and a member of a proud IIT family. IIT is great at the fundamentals. An amazing level of clarity and the sheer agility and speed of thinking. And I put a couple of examples here. One example is from JE, I think 20 advanced from 2017 or something, and it's calculate the angular momentum of that axle with two wheels with different radii. And it turns out it's not an easy problem, and I had to think about it a little bit, right? And I teach dynamics. It was wonderful, and to have your, as we used to say as kids in IIT, or preparing for IIT, getting your funda straight. That is profound. Let's not lose that. I'm not suggesting that. And I won't play this video, but this is a video of an IIT grad at MIT walking around challenging MIT students to solve problems. By the way, they do better than you expect. They're not floundering. And I'll explain why. I was actually surprised. They do, they struggle because they haven't been through that level of coaching, or they haven't been through that level of practicing. But they do okay. But the result of this, lest I sound as if I'm complaining about IIT, the thing that we cannot question is the sheer success of IIT graduates. And I put 3 examples here just because they're in the news recently. But the men and women of IIT have done well around the world. And this is something that I think IIT can take a great deal of pride in. But what do we do specifically? So I will make the argument that we do a good job with something I call textbook modeling. And that is that JE example I put up, right? Now I want to contrast that with real world modeling, which is something I'll come back to in a bit, which is, a different kind of cones, right? This is a cone that is, it's 2 conical rollers doing some sort of sheet metal work. It's actually not sheet metal, but they're forming a conical something or the other, right? Like a funnel, right? When you get to modeling things like that, something new, de novo, right? It doesn't fit into the first model. But, most engineering doesn't do that. Engineering is really focused right now, for the reasons of clarity of thought, on what I call textbook modeling. The second thing engineering education does quite well, and IIT does spectacularly, is good mathematical understanding. And what I mean by that is, really mastering Resnick and Halliday, and beyond that, mastering, the great math books that underlie it. And I think one of the things, and I don't mean this as a left-handed compliment, although it will appear so, is we're really good at teaching symbolic manipulation, really complex equations, integrations, things like that, right? In fact, one of my grad students, Sriram Krishnan, who was an IIT Madras graduate, was the MIT integration champion. We had the integration B for 3 years in a row. Really fantastic. I mean, that's hard to replace. But I want to ask a fundamental and, shall we say, candid question. Do we really teach intuition? And I want to spend a few minutes on that. You see, it is good to be able to crank, but it is not enough. And I'll make the argument that intuition is a profoundly different thing. So what is intuition? Many people can manipulate entropy, but in my view, the vast majority of people who understand entropy, in fact, even faculty, and I'll tell you a joke about it, don't actually understand entropy at the deepest level. I remember when I came to MIT as a young professor, I once decided I didn't get entropy. And I'd used it, but I didn't get it. I would say isentropic, I would say quasi-static. I was, what does it really mean? Delta Q over T. I didn't get it. So I'll tell you what I did. And I figured it out finally. And I barged into one of my senior colleagues' offices and I said, hey, I figured out entropy. He says, close the door. I closed the door. He says, now explain it to me. Because he had the courage to admit he hadn't gotten it either. So first of all, there's a courage that goes into with things like entropy, with things like intuition. What does it mean to really get it? I'll talk about it more in a second. We've all done linear algebra, positive definite matrices. Do people know why it's called a positive definite matrix? Or is it just something, it's a definition, vector, matrix, vector, what comes out is, why is it called a positive definite matrix? Right? What is the intuition behind it? Lagrange multipliers, and I'm using some arcane examples here. I've seen it taught again and again and again. But what is it really? What are those multipliers? Where do they come from? Right? As opposed to just doing some symbolic stuff and saying, we call those Lagrange multipliers. There's actually an intuition behind it, right? Or eigenvectors, the determinants, or the Laplace transform, or the Fourier transform. And how is the Laplace transform different from the Fourier transform, right? Laplace goes from 0 to infinity, Fourier goes from negative infinity to infinity, Laplace goes e to the power of minus st, where s is a complex number. That's the multiplicative element in the integral. Fourier is e to the power of I omega t. What's that? Right? E to the power of st, I'm sorry, right? Why are they different? Why do we do one and not the other? So when I tried to figure out entropy, I went on this little crazy mission, and I finally found the book that explains it. Actually, a guy called Arya Ben Naim, and he has this book called A Farewell to Entropy and he talks about statistical thermodynamics, information, amazing stuff. And you may agree with him or not, but by the way, he has I just saw this when I was preparing this deck, a new book out that he says, we have fundamentally screwed up entropy. Okay. Now, this book just came out. I did this work 20 years ago, straightening out my own fundaus on entropy. Now, I haven't read the book, but the point is to have an understanding where you can really sort of manipulate it instinctively, right? Fourier transform. This is called a read tachometer. I'm just going to show you this video, okay? It's this guy talking about
Writing's not that
Oh,
easy,
sorry.
but Grammarly can help.
Sorry.
This sentence is grammatically correct.
There you go.
Gentlemen, welcome back to the shop today to treat Especial. We got some old school, cool industrial gear. This is a tachometer from a bygone age when you didn't need electricity. There's no electrical connection, no batteries, nothing at all, and yet still it functions as a perfectly serviceable tachometer. If you're anything like me, you got a special place in your heart for real ingenious mechanical contrivances. This thing is brilliantly simple because one, as I said, you don't need electricity, but two, you don't actually need to come into contact with any shafting or anything like that. Behold, we can tell that this compressor is running at 31 to 32 100 or 1,000 ripams. And we also have a harmonic there at 45. Let's have a look.
So, by the way, this is where an IIT engineer can tell you that he had got a couple of things wrong. By the way, he calls it electricity. It's a joke. He got a couple of things wrong, but the concept is beautiful. Basically, this read tachometer is a bunch of tuning forks, and it just picks up the frequencies where there's resonance, and that is sort of the energy content in the frequency spectrum, right? And of course, this does it in RPM, but you can do it in omega, right? And he got it wrong because I think he got the harmonic and the actual frequency mixed. But the point is, it's a beautiful way to teach, right? Lagrange multipliers. If you go to Wikipedia, there's a beautiful way to explain it. If you have a constrained optimization, and these are the sort of the ISO level planes, and you have a constraint, you have to look for the place where they're at 90 degrees. It's tangential. That's where it gets maximized. And it turns out that's where the Lagrange multipliers come out of, right? But what we don't do is spend time on that because we want to do the problem, solve the problem, crank it, move on. I'll explain why this is very important in a few minutes. A positive definite matrix is like a positive number. A positive number, if you multiply it by another number, it either grows bigger or smaller, but the sign doesn't change, right? So if you take the positive number plus 3 and multiply it by -1, you'll get -3. So -1 became -3. The sign doesn't change. A positive definite matrix is the same thing. It's a matrix which transforms a vector in such a way that its sign doesn't change. In other words, the dot product of the final vector with the original vector is always positive. And a negative definite vector matrix is like a negative number. That's where it comes from. Just basic history. Fourier transform, you want to learn about it? Check out this guy called 3 Blue, 1 Brown. It's a channel on YouTube. Grant Sanderson, he used to work for Sal Khan. He's a Stanford undergrad. I know him quite well. He produces the most spectacular videos. Okay? Determinant, it's a sign volume of the original matrix. It's a simplistic way to say it. A Laplace transform. Well, I mean, most of you know it, but it reconstructs signal, decaying sinusoids. Reconstructs a signal in terms of decaying sinusoids, whereas a Fourier transform reconstructs the original sinusoid, so the full sinusoid. So anyway, the point I want to make is we undervalue intuition. We bulldoze over it. But to me, what is intuition? Intuition is when you can manipulate thoughts unconsciously. It's in your brain. You can't stop thinking about it. You know, entropy, when you really understand entropy, and of course, entropy comes from two different perspectives. One is thermodynamics and one is information theory, and those two haven't been bridged really well. That's what that gentleman, Ben Arian, talks about. But when you really understand something, you can dream about it. And I've had at least 2 or 3 patterns that have come out from dreaming about things, right? Because you become so obsessive about it, it sort of gets into some inner recesses, maybe the motor cortex of your brain, and you're dreaming. That is intuition, when you really get a feel for it. And there's a great example of this, actually. This gentleman is Kekule. Kekule discovered the shape of the benzene molecule. Until then, people thought all these molecules are open chain. I believe that's what happened. And he dreamed of a snake swallowing its tail. It's called an Ouroboros in Greek. And he woke up, you know, sort of that eureka moment. And he said, oh my God. And he came up with the aromatics, right? The whole aromatic concept, toluene, benzene, all that. Intuition is underrated, but I want to give you a couple of quotes. Steve Jobs said, intuition is a very powerful thing. It's more powerful than intellect. And yet we suppress it. And this is in engineering education, actually, right? Einstein has this beautiful quote, the intuitive mind is a sacred gift, and the rational mind is a faithful servant. But we turn it upside down, and then we suppress it. Now, we don't understand, or we didn't understand intuition, but we're beginning to understand it now a little bit, right? It is real. It is, you can actually see when intuitive actions are taking place. It can also mislead you, right? All this vaccine, all that, it's sort of a false intuition. But if you can harness it, it is incredible. But we actually distrust it. Also, intuition is hard to test. So streetlight effect, that's what I talked about, streetlight bias, we ignore it, right? But this is what drives engineering success. So that is the first sort of emphasis I wanted to lay, and then I'll build on it, right? By the way, I'll give you a couple of examples. This is a fantastic example from one of my friends, Sanjay Mahajan. He's actually at MIT right now. So imagine I give you this, I'm asking you a question, okay? Here's a table, ignore the thing on the right. Here's a ball. I let it go, it's gonna fall down, you know, it's mass M. It lands on the table, and then it bounces up. And the question is, what is the force on the ball at this point? I can't see in the chat, but I'm assuming many of you will say mg, and that's right. What is the force on the ball at this point? Well, same mg, just happens to be going up, right? But decelerating. But Sanjay has done this, and I've done this. This is his invention. By the way, he wrote a book called Street Fighting Math, which is all of the intuition of math. I recommend it enthusiastically. He says, when the ball lands on the table, what is the force on the ball? And you know, very interesting. A lot of people get confused and they go, 2 mg, mg. And then he asks a question. He says, he takes a metal ball, right, which is, you know, about half a kilogram. And he says, look, put your hand on the table. Let me put that ball on your hand. Does it hurt? No. If it's 2 mg, let me put 2 of those balls in your hand. Does it hurt? No. Now, do you mind if I lift the ball by a meter and drop it on your hand? And immediately the answer is, yes, I mind. I'm going to move my hand. It turns out that the force is actually much higher depending on how rigid the ball is, because the ball has to compress, and in a very small period of time, it has to decelerate downwards and accelerate upwards. So the force is actually, its impact force is very high, right? If it's a soft rubber ball, it'll be slow. If it's a metal ball, it's high. So intuitively, you know that it's going to hurt if you just stick your hand there, right? So that's intuition. And connecting the body with the mind is another aspect of intuition. Another little thing on intuition, how we destroy it with our curricula. You know Hooke's law, stress, strain, Young's modulus, right? Everyone knows it. Okay, easy. And I'm using a mechanical engineering example here. That's 1D stress strain. This is what 3D stress strain looks like. This is the equation at the bottom. So what do professors do around the world in engineering education? They go, oh, bichara, the other bahut mushkil hai. This is going to be very difficult. We shouldn't go here. From here, we shouldn't go here. Let's do 2D. And they introduce 2D stress strain. And that is a mistake, because there is no such thing as 2D stress strain. You can have 2D stress, it'll be 3D strain. It's because of the Poisson ratio. You can have 3D stress, a 2D strain, you'll have 3D stress. And so in an attempt to simplify it, what they do is they actually may destroy intuition with something called plane strain, plane stress. It's a disaster. It takes courage to say, no, that's the wrong way to do it. And actually at MIT, we do not teach 1, 2, 3. We teach 1, 3 dimensions, and we teach 2D as an exception because it's actually more complicated. And those little insights take courage, they take gumption. And we have to focus on why we spend so much time doing stuff that is not intuition focused, right? And how we can fix that. Because intuition helps design. And I'm going to talk about that next under the context of reversibility. But my view is we have to focus on intuition. Okay, so with that, let me jump into the next piece. I talk about the real world and argue that it is cyclic. The real world throws up problems that are cyclic and complex. And I don't know if we really sort of are preparing our students for the challenges they're going to face with climate change and all the other crazy things that are going to happen in the next 2, 3, 5 decades, because they will be in charge of fixing some of these issues. Okay, so let's talk about that. How does engineering flow today? You have the fundamentals. In IIT Kanpur, if you really wanted to pay someone a compliment, you would say, "Wo to fundu hai." Right? It's a great thing. I mean, I take great pride in this. We are great at the fundamentals. I love it. Okay, principle 1, principle 2, principle N. Okay. So how do we teach today? We teach with textbook problems. And I've already described some textbook problems. And textbook problems look like this thing, right, that I showed you earlier, which is, by the way, a great problem to getting your fundamentals right. And then we tell students, we tell them, reverse model the textbook problem. In other words, create a model out of it, right? And then forward crank and solve the problem. I'm going to tell you that the world is not textbook problems, but I think we all agree with that, but I'm going to tell you in what way, in my view, it is not. You see, textbook problems have this nice convenience of being quite easy to sort of go back and forth and being one-on-one. Okay, a physics textbook problem only shows up within physics, and even within physics statics, the textbook problem is only statics, it has no dynamics in it. A dynamics textbook problem, because you want to teach, I don't know, angular momentum, it has only angular momentum connections. It doesn't have anything else, right? It doesn't have Coriolis force or something, right? If it's kinematics, it has only one thing and not the other thing. So it's very convenient for teaching principles. But as the world evolves and engineers have to take on more and more difficult aspects of reality. They're going to confront real world problems. Now, real world problems are not as well behaved. They don't say, you know, Bichara, he's just learned, she's just learned angular momentum. I should only target angular momentum. They don't have that courtesy. They look like this, right? Rather than this. You know, that's the Mars rover, right? And there's dust, there's junk, you know, there might be an earthquake on Mars, who knows, right? And it's multiple wheels, it's not just two, different suspensions. Real world problems have the inconvenience of being like that. They go across principles, across chapters of the textbook, across textbooks. Now, just to contrast, it's not one-on-one, it's like that. And in real world problems, you have to then sort of iterate back and forth and solve the problem. So you have to be part chemical engineer, you know, you have to be part mechanical engineer, you have to be part electrical engineer, you have to be part, you know, business manager, part strategist, right? And that's a real world problem. We saw this with COVID. COVID is a real world problem in a nutshell for us, right? Except a massive one. But at some level, it's a technological problem. mRNA is a technological solution. Now, reversing the flow of thinking, if you want to solve the problem, requires something very fundamental, which is reversibility. How do you reverse something this complicated? Beyond a point, learning the Navier-Stokes equation or learning something really complicated sort of doesn't help. Beyond a point, if you want to reverse something, this is reversibility, you need high-level intuition. Lumped mass models. You need to be able to sort of say metrics. You know, I'm building an electric car. I don't know, I probably need about 75 kilowatt hours. You know, the density of batteries is so much. So it's going to be so many liters of battery. And it's going to be a ton of battery, literally 1 ton of battery or something, right? Is that even going to work? Maybe not. So I need to work, actually it turns out it can work. That's basically what Elon Musk did. And by the way, to Elon Musk's credit, for all the, shall we say, sensational things that people say about people like Musk and others, they think in those terms, and that's where the problems get solved. And I've seen him talk about it. You know, you can see he's thinking that way in those big picture, and he can reverse. And he's not afraid when it's necessary to sort of jump into the details, you know, the Navier-Stokes. So you need high-level intuition, plus you need low-level models. Not Navier-Stokes, but Bernoulli. Because that's the thing that can be reversed. When you go forward, you can do Navier-Stokes. But when you go reverse, you need high-level intuition and low-level models. It's the reverse of what we teach. Right? Happy Republic Day, by the way. I mean, it does look like the Indian flag. So, but sometimes something rather profound happens. And this is something that I've been trying to figure out for the last 25 years that I've been at MIT. What happens here that is different? When you're very problem focused, sometimes strangely, when you're solving the problem, you find the existing fundamentals don't do the trick. And you have to invent a new fundamental. And that's how Nobel Prizes come up. Right? New principles, new concepts in economics, and in physics, right? In math, that's where the Fields Medal comes up. In computer science, the Turing Award, right? I'll give you an example of a Fields Medal. There is something now, it's called compressed sensing. When you're sampling, when you're doing, for example, Fourier transform, etc., if you know that the space is very sparse, you can actually get away with much less than, say, Nyquist sampling. You can get away with much lower sampling because you assume sparsity. And Donohue at Stanford and Terence Tao at, I think he's at UCLA, figure it out. They're both Fields medalists. That's Fields medal level awards. So problems actually engender more fundamental discoveries, in my view. And if you actually look at the history of a lot of fundamental discoveries, they come from problem discovery, from problem exploration. And then the other thing happens too. When you start solving problems, when you start combining principles, you're solving one problem, you start discovering new problems, solving them, and finding new ways to solve sort of problems that are not being stated. And that is how we create deep tech industries. You know, I mean, if you take, for example, what's happened with mRNA technology, mRNA is the combination of our understanding of RNA and nanolipids into which they could be inserted. By the way, do you know, does anyone know why Moderna is called Moderna? Moderna is an MIT startup. It comes from the letters mRNA, Moderna, right? One of my colleagues, Bob Langer, was involved in the nanolipids piece, and together you come up with mRNA. It's a little bit more push. But the focus on problems is a very profound thing, and that jugalbandi, you know, between fundamentals and real problems is important. I'm not saying that the textbook problems are not important, but they're scaffolding. They have a place and a time, and they should go away once you're done. So real world problem solving actually goes like this. There's actually a great paper by a Caltech professor by the name of Robert Middlebrook. He calls them low entropy expressions. That guy I told you wrote a book on entropy. He would probably have a heart attack if he saw the word entropy used in this way. But he means this in the English sense, not in the physics sense. In the real world, as you know, as many of you know, you go forward, you go backwards, you go forward, you go backwards. All the backward motions are based on intuition and low-level models. I'm thinking Bernoulli, not Navier-Stokes. Forward is where you do the Navier-Stokes. And I worry a little bit in engineering education that if we don't teach especially the elite institutions, don't teach the reverse piece, we will train high-paid technicians. The other thing I'll say is that owning the problem, not the solution, is actually very, very important. In my view, if Indian problems have to become first-class problems for us to become, you know, we're already world-class, but to truly become world-class. And you need to master the problem before you can master the solution. There's this great quote from Einstein. If I had 1 hour to solve a problem, I'd spend 55 minutes thinking about the problem and 5 minutes thinking about the solutions. So even framing the problem is profoundly important, and creating the problem statement, right? And you know, if necessity is the mother of invention, India's got to be the mother of necessity. So there's no shortage of problems in India. And they don't have to be super glamorous, you know? Take something like concrete. I mean, it's such a profound question. Cement. You know, 7% of, or almost 8% of all CO2 emissions come from cement. And we're one of the biggest, India's one of the biggest users of cement. There's this Japanese technique called 5 questions. Ask 5 questions about any problem you see. For example, we know that, you know, this picture, this background is the standard. Actually, this is very similar to what's happening in my parents' house, which is, you know, seepage. Why is there such a big seepage problem in India, right? So ask 5 questions. Well, is it because we have poor technique? In which case, next question, why do you have poor technique? We need to train the karigars, we have to train the masons, right? Why they're not getting training? Because they learn from, you know, there's no training institute. You ask 5 questions and you explode the possibility of issues you can take on. Is there a dilution with sand, right? Okay, why is there a dilution with sand? Well, because there's a quality control thing, et cetera, et cetera. Did you know there's a sand shortage? Why is there a sand shortage? Well, let's examine that. There is a sand shortage because actually sand that's used in concrete has to be a particular shape. River sand works well and sea sand does not work well. Now, when you do this sort of 5-level thing, it leads to a deep understanding of problems and I think profoundly rewarding experiences in learning. And intuition, that cyclic thing, all those things can be put to test. By the way, after all the sand mining mafias in India and all the trouble and, the tragedy in Uttarakhand where a bunch of students from Hyderabad died because the people were doing some hera-fairy with the sand. It wasn't an Indian person who wrote the story of sand. It was this gentleman, Vince Beiser, who was actually a Berkeley graduate. He wrote a beautiful book called The World in a Grain. And he talks about how there's a sand shortage. And he's the guy who talks about how river sand is more valuable than sea sand, right? And so on and so forth. So if you just look there, Feynman said there's plenty of room beneath. I think there's plenty of problem solving and opportunity beneath. So next, I'm going to talk about the pedagogy of the future. What do we need to do for the future? And then I'll end in a few minutes. I'm okay for time, Ambuj? Another five minutes or so?
Absolutely.
Thank you. So I'm going to now talk a little bit about the pedagogy of the future. So the way that education works today, you have an expert, and then you do something called cognitive task analysis. That's actually the formal way to do it. We'd actually do that. But the right thing to do is to pull out insights. Then you take the insights and you turn them to a curriculum. And you take the curriculum and you do instruction, and that's how the learner educates. And this is what we can put in a course, right? Into an online course, etc., etc. So this is the explicit curriculum that most of the world, most of engineering education is focused on. What we do, for example, is, if you're modeling a textbook model of those two wheels on an axle with one wheel which is has a lower diameter, how does the expert do it? Well, they say, okay, you do a free body diagram, or you break it up into pieces, and you find the axis you're going to use, you calculate the angular moment of inertia, all that stuff. That's an explicit curriculum. But the key thing that we are forgetting is the variety of learning actually happens through the implicit curriculum, which is coaching. And if I look at the education at MIT, and especially in graduate school, this is where most of the learning happens. A lot happens through explicit, but implicit is where the magic really happens. Would you ever take a flight with a pilot who only studied with an explicit curriculum but never got to apprentice with another pilot? Would you go under the knife of a surgeon who never did coaching and apprenticeship? You wouldn't. It's like that thing I showed you about putting your hand on a table, right? And me dropping a ball. Intuitively, this is important. This is what parenting is, by the way. Your child didn't have an explicit curriculum when you trained your child or trained another child. It was all implicit. You send them to school, but parenting is super important. It shapes people. But this has been lost. And this is what the kitten got from the cat, right? And so we, as an educational fraternity, and fraternities is a gender term, so I'll say an educational community, need to take on implicit learning and the implicit curriculum much more, dare I say, explicitly. Engineering pedagogy has to change. We have to re-emphasize intuition. And if you want to work on intuition, you need classroom time. And we, as I've said in other talks, I won't bore you with it, we squander our classroom time with one-to-many lectures. And this is where online comes in. Flip the classroom. It's ridiculous that the classroom, not in IITs, but in many today, vast majority of engineering education, the professor is reading from the textbook effectively, right? But we should use that precious time, which, by the way, COVID has confiscated from us. COVID has confiscated that precious time from us. So when we get it back from the vice-like grip of this pandemic, let's make it count and do the things that we need to prepare the creators of the future, right? Case studies, real-world problem-solving challenges, simulated problem-solving through exercises, reverse modeling, forward modeling, that lump parameter, intuition, right? And then expert sessions. How did you think about it? Mr. Sridharan, when you thought about the Delhi Metro, you made some decisions. For example, you made, a different gauge. You thought about it differently. The quality is very good. It's world class. How did you think about it? What was in the back of your mind? Hard to test, but very hard to put a value on it. It's invaluable, right? I'm a big believer in co-op programs where you actually go work in a company. You know, the University of Waterloo, which is this great university in Canada, it's only 50 years old, but they've risen up in the rankings. Students spend almost 50% of their time doing co-ops, means they're interning in companies. Hackathons, problem framing and solving intensives, and gradually leading into more and more open problems, as the cat did with the kittens. My own journey, by the way, when I came to MIT, as Ambuj kindly said, I'm a mechanical engineer. I got into RFID and I had to teach myself. You know, I taught myself RF, signal processing, protocols, you know, semiconductors, analog electronics, manufacturing and standards. You know, we developed a consortium, understood the business. You know, I was writing papers in business journals, you know, applications, the use landscape. You know, then we built out standards and standards body. And there were more than 10 billion RFID tags last year with our protocol on them. But all of it was intuition and low-level modeling, but using it appropriately and mixing and matching, right? Another thing I want to also just emphasize, this is one of my last slides, is being world-class is a science. I've never been a big fan of the jugaad thing, right? It's a great sign of our creativity. It also shows that we limit ourselves to short-term solutions. These young people I see in mechanic shops who are doing jugaad, think of the magic they could do if they were given the discipline and the time and the luxury of and an exposure to what it means to be world-class. And I have 3 examples here. One is Embraer. Embraer is a Brazilian airline manufacturer. Out of Brazil comes one of the 4 great plane manufacturers in the world, aircraft manufacturers. If I fly in the US, 1 in 5 or 6 flights is an Embraer jet. By the way, it came out of a university called ITA, which MIT helped set up. And ITA is the university that supplies Embraer. So it is a world-class company. How did it come out of Brazil? Right. The second is, this is called Rocket Labs. This is some kid in New Zealand who has basically one of the most advanced rocket companies in the world, along with SpaceX. He's named for low cost, very efficient, very lean rocketry. Right. And of course, our own ISRO and then Antrix. Right. These are case studies. How do you become world class? How do you look for best practices and best in class? How do you study the techniques, attitude, and approaches of the world's best? You know, this is what Neeraj Chopra did with his javelin, right? And he had a great coach, by the way. So coaching matters. Technique, coaching. Technique means, you know, interval training, exercising, and then coaching. And then finally, an intuitive and insightful understanding of the internal logic. But then finally, most importantly, having the gumption and the ability to do something new that is world-class rather than mimicking what the other person is doing. And that's when you break away. And these are all examples of that. Right? Embraer went for the mid-size. They didn't try and do what Boeing does. And they had the gumption to do it. Not small, not big, mid-size. Right? Of course, we know the story of ISRO and then eventually Antrix. And Rocket Labs went for a different niche. How do you do something that is going to be best in the world? Gold medal. And that, I think, is a compulsion we need to develop. So I'll just end with this. You know, students and faculty and experts of problems need to come together. It can't just be students are a sheet of paper, professor writes on their head, fills it up. They forget after the class, but they're not given the golden opportunity to be creators with intuition and the low-level insights they need to take on reverse problems. But I think if we have an opportunity in education to rethink it, and engineering education must change, and we need to teach like cats more than we do today. And we really can be limited by our perceptions of what it means to test and, you know, all that stuff. So I'm going to end here. Let me see if I can take this down. Ambuj, back to you. Can you hear me?
Yes. Thank you very much, Sanjay. That was absolutely fascinating. Let me actually maybe just start with a question myself while other people are putting questions into the chat box. I'm just curious with this kind of the kind of things you're talking about, focus and intuition and problem solving and all of that. How is this being received at MIT in terms of thinking about uh, how what this means for how the curriculum must change? I mean, how receptive have people been to that kind of these kind of questions of not maybe not totally rethinking the curriculum, but certainly some key aspects of the approach to curriculum and
Actually,
pedagogy.
yeah, I mean, you of course are an alum, so you know it well, but MIT actually is quite open-minded about this stuff. And in fact, it runs deep in its blood to think this way. So for example, every robot competition that you see where you see these robots fighting each other, cutting each other up or whatever, right? They all started from a competition at MIT called, at that time, the course was called 2007. Actually, it's still called 2007, License to Design, 007, right? And so this whole business of projects, we have something called the Undergraduate Research Opportunity Program, where students actually apprentice in research labs where they're solving real problems. In fact, right now at MIT, we're in the last week of something called the Independent Activities Period. It's a winter 1-month period where students get to do anything they want, electric vehicle team, this, that. So it's actually very much celebrated here. In fact, the MIT logo has a book and a man with a sledgehammer, right? That's how deep it runs inside. But actually, I think MIT's regressed and now is trying to go back in that direction. Over the years, lectures invaded and content became king, right? And now we're going back to making sure that students get it and get more intuition. A lot of our students are coming in saying, I want to address a global challenge. I don't want to be merely an equation cranker. So some changes have occurred, but I'd say MIT is quite natural.
Okay, thank you for that. By the way, before I go on to the questions, I did want to say that kind of it's interesting what you were talking about. The people who actually study innovation have been actually thinking about many of the things that you said. In fact, there's a very famous paper that I give to my students by Klein and Rosenberg that says you move away from the linear model of innovation to the more design and feedback oriented. It's a very, very, very famous paper. So I think you're right that in a sense that's really how innovation happens in the real world. It's a much more messy process of the kind you pointed out. So I think that point is well taken. Let me just bring some questions up. So I guess one of the questions is, what might be actionable steps? I think you gave some of those already at MIT, but I think the question is, in the Indian context, what is it that you would think about as kind of maybe somebody's asking on YouTube, what might be the most actionable items that you might suggest?
Yeah, I mean, again, there's many things I've said, but let me talk about intuition, right? Intuition, I think, is a very fundamental aspect of this. So I say, for example, I teach dynamics and I teach damping, right? In one lecture, I talk about, after they do rigid body dynamics, we do damping. And in damping, there's the mx double dot plus cx dot plus k is, forcing function. So the C factor. So what I tell my students is, and you teach critical damping, and I say, I want you to spend a day with these X-ray glasses where you see damping everywhere. I want you to observe the world and look for damping, right? And not all of them do it, but a lot of them do actually. A surprising number do. And they come back to me with examples like, oh, when you open a door, the thing that closes the door, so that the door doesn't slam, it has actually a very interesting mechanism with a damper built in, right? Shock absorbers in cars, in trucks, in construction equipment, your chair, right? And, especially sort of not a wooden chair, but sort of more office chair types, right? And they start thinking about it. And over time, they realize that damping is inevitable in everything. And you develop that intuition because now you're looking for damping. And later in life, when you're not looking for it, you will see it because, and it may be useful, it may not be, but you see it. So that's sort of one thing, which is putting on the lens of viewing everything that way. Entropy is similar. How do you capture entropy? Have you just seen an isentropic process? Have you seen an irreversible process? What is reversibility? What are some examples of reversibility, right? Why is friction irreversible? So that's sort of one thing that I do. The second thing, again, it's a sort of a thought experiment, but again, I ask my students to do it, is to frame problems, which is you're going around looking at things and you're going to see problems. There are lots of things that bother you or irritate you, or you think you could do that better. Make up a solution. Just do it. Make it compulsive, right? But to solve that problem, not a textbook problem, that problem. And so these are all sort of habit-forming things, right? And I think, again, if I see the students at MIT, because they have good intuition, we do work on their intuition. By the way, when I gave my talk, I said they did better in the IIT exam than I expected. It's because of the intuition aspect, right? And this problem framing, I think so the key is to make it a compulsion, to make them lenses that you wear, modes of thought.
So I'm going to build on that and actually just, I think, kind of ask a follow-up question. I think you and I have talked about this, but if you are to go with what you're saying, Sanjay, then some of this actually has implications. The implications start even before engineering education, right? The implications really then go back into school education of what is it that we are doing in schools and the kind of training we're getting. But because in a sense, I think it's difficult to imagine that, also you're right. I mean, although one could imagine kind of training yourself to really develop that intuition later on, but in some sense, it would be much better if it really started at a much early age. So have you been thinking about that, about what the implications really are for school education, for the kind of things you're talking about?
Yeah, and I have thought about that quite a bit, about school education. A lot of times schools have already trained the young people to think in a certain way by the time they come to college. So just as Professor Rao said, sometimes the faculty are the problem, they don't want to change. Equally, actually, students themselves have been brainwashed into thinking a certain way. So schools have to change. But that's happening already because of Sal Khan and people like that. Some of the top schools are changing the way in which they teach. They use Khan Academy. There's actually an MIT company called Quizlet, which 50% of all high school students in America use. And so they show up to the classroom and the teacher finds that the students know stuff, so they have to make something up. So they flip the classroom naturally. In fact, my daughter's Spanish teacher realized there was no point teaching Spanish in class because students had already sort of learned it on their own. And so he made them all write plays and act them out, which is very different, and actually made it a very popular class. He won an award for it. So I think in schools in certain parts of the world, it's changing. Are the patterns too set to change? I think they can be changed. I think the patterns can be changed, but it doesn't help that schools are sort of stuck in that world. No doubt about that. So I think, yeah. So in fact, at MIT, we have a big effort now on K-12 education and things like that, where we're trying to bring in more of a maker mentality to schools.
Thanks. One more question from YouTube. The question is Jugaad not implicit learning?
It is. But remember, I said you need implicit and explicit, right? So I'll give you an example. Jugaad is, I see something not working really well here. I see something broken, I'll weld it. Professor Anil Gupta, the famous founder of Honeybee Networks, he's a good friend, and I work a little bit with him, and he gave me this example. But Jugaad is, I just welded it, it worked. But what this young, bright person didn't learn was, well, you actually welded two different metals. Embrittlement occurred, so it'll break eventually, crack propagation, right? You could have used a different welding technology, not an oxyacetylene torch. You could have used this other thing. So that's what I mean. I mean, it's not, I don't want to kill the spark of jugaad. The point is, how do you become world class? What's the best technique? How do you think about it? How do you see these are two different metals, right? How do you make sure that you get the right material to actually join two different metals? It actually turns out to be not that trivial. You get corrosion if they're two different metals with different electropotentials. If you weld a zinc, you might get something called zinc fever, which is a sort of a reaction to the zinc. You know, so yes, jugaad is a spark, but should we not direct it? That's where I'm going with this.
Yeah, and maybe related to that is a question again in the chat about I guess the role of design thinking in the future of engineering education. You know, points things like working on wicked problems, spending time framing problems, hands-on learning, experiential learning. So what's your thought on that and experiences with integrating design thinking into the engineering curriculum?
So design thinking, I mean, I have mixed feelings. On the one hand, it's a really fantastic thing. I mean, obviously, I'm very positive on it. But the problem with design thinking is a lot of it has to do with like consumer goods and things like that, right? How do I make a better skillet or better, you know, something else, right? Like, you know, a lot of real world problems are wicked and tough in the sense that you need to, in the end, you may have to do some deep tech. You may have to develop a material that is, you know, super hydrophobic, and then that solves the problem. If you look up, in fact, one of my colleagues is across the hall from me, Kripa Varanasi, is an IIT Madras graduate. He's a professor at MIT. Check out Varanasi Lab and look at what they do. I mean, this is tough stuff. So, so I'm in favor of design thinking if it can be expanded to not shying away from the really difficult technological problems that you need to solve. The good news is if you can solve it, you've unlocked a huge potential, right? As opposed to making up a technological problem that may or may not be applicable in the short term. That's also worth it, don't get me wrong, right? I mean, we never knew nanolipids would be useful, right? Or nanoparticles would be useful until much later. But there are much more pressing problems that are just there, so why not take them on, right? So anyway, so my point about design thinking is, yes, it's a good idea, but it's been applied mostly to a way of thinking with consumer stuff. And I think deep tech and wicked problems can benefit from the same level of attention.
Thanks for that. Okay, one more question. It's asking the question about the contextual difference between an IIT and an MIT in terms of the motivations, the backgrounds of the students, the context is different, social conditions are different. So what implications might that have for pedagogical approaches? Or do you think there is some notion of universality in some of the things that you're talking about, regardless of the very different conditions?
No, it's a good question, and it's a delicate question. I mean, I've got to take it on carefully. I think that question was from Arudra,
Arudra, yes, it is from Arudra.
although he won't admit it, is a relative of mine. But anyway, I think that, I mean, look, we can fall into a trap and say there are elite schools where you do elite stuff and let everyone else do something that's more sort of, you know, vocational, right? That's a trap I'm very wary of. I mean, certainly it's true that if you go to more of a commuter school and you're just trying to get a job, you know, you want more skills that can apply tomorrow. But I think there's a sort of a, you know, the level of intellect I encountered at IIT, frankly, even at MIT, I mean, it's there, but it's a different kind, right? I mean, so I would say IIT and MIT, I would put them in the same category. Tsinghua, you know, Ecole Polytechnique, ETH Zurich. I mean, you can't really separate the undergraduate talent there. Now, and I also think there's a level of universality in problem solving, because in fact, some of the issues that I've raised are even worse in the mid-tier and lower-tier engineering schools. And problem solving is very essential. What I find in the United States is this sort of mentality of being a little bit more sincere and candid about what you understand and what you don't is quite pervasive. I see it even in mid-tier and even lower-tier schools. It's almost like a mindset. I want to give you an example, actually, which also connects to the K-12 question. So my mother was visiting when our daughter was, you know, 7 or 8 years old from India. She was visiting from India, and she's a high school teacher, was a high school teacher. and she volunteered at the local high school. Now, as you know, there is this well-known contempt that a lot of expats have in America that, oh, they don't teach anything. You know, the kids are never taught what the capital of Mongolia is. It's Ulaanbaatar. They have no idea. They have no idea about the world. They don't learn anything. They don't memorize anything. Anyway, my mother sort of volunteered, and she one day she told me, you know, interesting, today in school, the students were asked to build cardboard castles. Yeah. And she said, I now noticed something very profoundly different. If this were India, we would have given them a big quiz about the when castles were first built, and label all the parts and something else, right? Capture the volume of the castle, who knows? She says, here, the kids were asked to build these castles out of cardboard and then figure out under certain scenarios, you know, what the turret would be used for, you know, what the gate would be used for, you know. So it was much more sort of insightful and intuitive. So she said, in her view, the students learned more in this sort of discovery-based approach, where they were trying to use the castle, than a labeled approach, which you'd have seen in any other part of the world. So I actually find it quite pervasive, and I think there's a universality to it a little bit.
Thank you. Thank you for that. One more question, again from the chat box. It says, what does it take to transition from TBP, the textbook problems, to real-world problems? And would appropriate modeling of assumptions and premises help?
Yes. Yes. I think what you have to do is textbook problems are more, they're very necessary. It's like scaffolding. Okay. So the way, let me explain. The best way to teach cycling, learning to ride a bike, is to have training wheels, you know, those little 2 extra wheels on the bicycle. But what you do is every day you lift them a little bit and eventually you remove them. The best way to teach swimming is to put flotation straws on the learner's arms. And every day you remove 1 straw. And eventually they're not getting any straws. So that is called a fading scaffold. So what you do is you put a scaffold and you remove it. And this is well known. This is a lot of cognitive psychology. And that's what the cat was doing to the kitten, by the way, right? Dead mice, half dead mice, live mice, right? It's the same thing. And that's what every parent does, right? You make it easy initially and then increase degrees of difficulty. So we have to do the same thing with the textbook problems. Then you throw in one more complication, right? And you show that the closed form solution, it becomes difficult. And so now you start doing some holistic intuition. Then you lift the problem some more. Then you lift the problem some more. And then you give them an open problem and you let them go at it. And they'll struggle because some of these problems are unsolvable. So that scaffolding is the way you go from textbook to open problems.
Thank you for that. One more question. It's about evaluation. That if one thinks about this kind of a new pedagogical paradigm, what does that mean for how do you evaluate?
Great question. Great question. And I'll give you an answer, which at some point I need to sort of write up. Success is subjective, and success comes from subjectivity. Intuition is subjective. We don't trust subjective. We go to the objective. Observational bias sets in, and we end up under a streetlight looking for something that never fell under the streetlight. So let me repeat that. If we don't have the faith to make subjective judgments, we will not get subjective success. And unfortunately, what I'm saying to you is that the success lies in the subjective. So at MIT, even in exams, even with undergrads, we keep alive subjective. Even in admissions. And people always complain, oh, it's not objective, it's unfair. And there's probably some unfairness, but the magic is in the subjective, and we're all terrified of it. So you just put your finger on what I think is one of the great one of the really challenging paradoxes in education, right? The streetlight phenomenon comes from there. But if you look at life, a lot of success is subjective, right? How do you judge a movie? How do you judge, why is someone a star? Sports is a weird thing. We make up sports is sort of made up objective measures because it's easier to measure, but life is not. Sports is a simulation, right? You can see a batsman score, but even there, the batsman who's going to, or the bowler is going to perform when the chips are down, right? I mean, if you compare Dravid and Tendulkar, right, or Kumble and others, Anil Kumble had steel, right? That's a subjective measure. So yeah, it's hard to measure, but it's subjective measures.
All right. I think maybe we can, there's a whole bunch of questions that you've answered. Thank you very much. I think we're kind of coming to the end of the talk. So let me just hand it back to the Dean Academics, Professor Shantanu Roy. Shantanu, back over to you. Thank you very much, Sanjay, for that really lovely back and forth with the questions. Thank you so much. Shantanu, over to you.
Yes, thanks, Ambuj, and thanks, Professor Sarma. It was a very, very enlightening talk. And I just had one small kind of remark or question that many of us, and all of us, I guess, would have been fortunate to have teachers who somehow blended the intuitive learning along with the, if I might use the term, prescriptive learning, right? So they would be teaching Navier-Stokes, they might be teaching Bernoulli's equation, but they kind of scaffolded, to use your term, with real world examples, and we would kind of understand what was the purpose of learning friction factor, for instance, which would be otherwise a very abstruse concept. But because of those examples, you kind of develop that learning. So would you not agree that a lot of what you said in many ways is already a part of good teaching? I mean, in any institution, it is not about whether they're the Ivy League institutions or MITs or IITs or whatever, but it would be anyway going on. Would you not agree to that? Do you think there is what you really have been kind of propagating is good learning, good teaching practices, with relevance to real world problems?
Yeah, no, I think that's fair to say. I mean, I think a lot of these things can be mitigated by good teaching, but I think there's a lot more than that, because real world problem solving, exposure to real world problems and experts, right? I'm talking about capstones, and I'm talking about every year having a course which is, okay, you learn these 3 things, here's where it shows up, right? Number 1. Number 2, I'm talking about the flipping the classroom. So the idea is the professor doesn't waste time giving the regular lecture and focuses entirely on problem solving and intuition in a context, using context that come from the real world. So at some level, in the microcosm of a course, a good professor may do some of this, but their degrees of freedom are very limited. It might be a few sort of comments here and there, I'm talking about a macroscopic, cross-course, cross-curriculum rethinking, where less is more, and real worlds are sort of infused into it.
Okay, wonderful. So thanks, Professor Sarma, on that note, and we would also be reaching out to you for further discussions on this. There were lot of questions which I think haven't been addressed, but we would take your time for it at some appropriate occasion to discuss more with you. So thank you for your time today. Thanks for this early talk to all of us, and very fitting for our Foundation Day lecture. So thank you so much for your time, and thanks for answering all the questions. Goodbye.
Thank you, Professor.
Thank you.
Sanjay. Bye-bye. Thanks. Thank you so much.